So imagine you buy this like $100,000 sports car, right?
Nice.
Yeah, it's an absolute engineering marvel, beautifully designed, incredibly fast. But a week later, the engine starts making this really weird rattling noise.
Uh-oh. That is never a good sign.
No,
Yeah.
definitely not. So you pull into the only nearby repair shop and you realize this horrifying truth. Every single mechanic there speaks a completely different language than you do.
Oh, wow.
Right. You point at the engine, you try to like mimic the rattling sound, but they just stare at you. I mean, you have the hardware, you're physically standing right next to the person who can fix it, but you are completely paralyzed because you have, well, zero ability to communicate.
It's just absolute gridlock.
Exactly.
And, that exact frustrating scenario is precisely what would happen to computers without network protocols. Just having a physical wired or wireless connection, it just isn't enough. Devices need to know exactly how to communicate.
Welcome to the Deep Dive. Today we are digging into a presentation deck titled CCNA Introduction to Networks, Module 3, Protocols and Models. And our mission for you today is to basically demystify the invisible rules of the road that allow billions of wildly different devices across the globe to just talk to each other seamlessly.
Yeah, because to establish that foundation, devices need 3 essentials before they can even try to talk: a message source, a message destination, and a channel.
Okay, let's unpack this, because now that we know why we need rules, let's look at what those rules actually look like.
Right.
The source material uses this great analogy of sending a physical letter. Just like a letter needs, a proper address, a specific format, and a delivery process to actually get to someone's house, a network message needs structure.
It really does. There are essentially 4 basic agreements needed before any communication even begins. You need an identified sender and receiver, obviously.
The addresses.
Exactly. Then you need a common language and grammar. You need to agree on the speed and timing of delivery. And finally, you need some sort of confirmation or acknowledgement that the message was actually received.
Okay, so let's push back on that common language part a bit. The text talks about this concept of message encoding. And I kind of think of this like human thought, right?
How so?
Well, a human has to convert an abstract thought into spoken words, which is encoding. And then the person listening has to hear those words and reverse the process to understand the thought, which is decoding. Is this basically what the network is doing, just with, ones and zeros instead of human language?
That is exactly what it's doing, but it gets even more granular because it's a physical transformation. The protocol dictates exactly how your device takes those logical ones and zeros and encodes them into physical signals, like light pulses in a fiber optic cable or radio waves if you're on Wi-Fi.
Wow, okay.
Yeah, and beyond just the encoding, the protocol also handles message formatting and message size.
Message size, meaning you can't just send the whole thing at once.
Right, exactly. Long messages have to be broken into smaller, manageable pieces. It's just like how humans speak in sentences. If I just talked at you for 10 minutes without taking a breath or pausing, you'd be completely overwhelmed.
I would definitely tune out.
We all would. So networks do the same thing. They chop the data up so the receiving device can actually process it piece by piece. Plus, it gives other devices a chance to use the channel.
Which brings up a huge point. Knowing how to build the message is one thing, but what happens when you actually try to send it across a really crowded network? Like a busy coffee shop Wi-Fi.
Oh, the coffee shop is a perfect example of why message timing is so critical.
Right, because there's so much traffic.
Huh.
So the text breaks down message timing into 3 key elements: flow control, response timeout, and the access method.
Yeah, and flow control is basically about pacing. It dictates how much information can be sent and how fast it can be delivered, so a super fast sender doesn't just drown a slower receiver.
Makes sense. And response timeout is just how long the device waits for a reply before giving up.
Right, exactly. But the really interesting one is the access method. This determines when a device is actually allowed to send data.
Okay, I have to ask about this because the text mentions collisions.
Yeah.
Is this access method thing basically the digital equivalent of an awkward Zoom call?
Wait, what do you mean?
Where 2 people start talking at the exact same time and then both realize it, they stop, it's super awkward, and then they both have to politely back off and wait a second before trying to talk again.
That is a brilliant analogy. Yes, that is exactly what it is. When 2 devices try to transmit on the exact same radio frequency at the same millisecond, their signals physically interfere. It's a collision.
So how do they handle the awkward Zoom pause?
Well, they use specific delivery and access protocols to avoid it. They essentially listen to the network to see if it's clear before speaking. And if a collision does happen, they use random mathematical back-off timers so they don't just step on each other's toes a second time.
That's amazing. Enforced randomness.
Yeah. And this all ties into how messages are addressed to avoid confusion in the first place, using 3 different delivery methods.
Unicast, multicast, and broadcast, right?
You got it. Unicast is just a simple one-to-one delivery. One device talking to one specific destination. Multicast is one-to-many, but only to a selected, targeted group of devices.
Okay, but then there's broadcast, a one-to-all delivery. If we're so worried about traffic and collisions, why would you ever want a protocol where a device just yells at every single other device on the network?
It sounds chaotic, I know. But if we connect this to the bigger picture, these timing and delivery protocols are basically the invisible traffic cops keeping the digital infrastructure from crashing. Broadcasts are noisy, yes, but they are essential for network discovery.
Like when a new device joins.
Exactly. When a new computer wakes up on a network, it doesn't know who anyone is. It has to yell, "Hey, who handles the internet routing around here?" so the router can reply back. Once they find each other, they switch to the quiet, one-to-one unicast.
Okay, that actually makes perfect sense. The megaphone is just for introductions.
Exactly.
But knowing all this, it seems like one single rule couldn't possibly handle all these different tasks. Checking for collisions, managing flow, finding the router.
It can't. That would be impossible, which is why networks use what we call a protocol suite.
A protocol suite.
Yeah, it's essentially a team of rules working together as a stack. Every protocol in the stack has a very specific, isolated job.
Okay, let's trace an example down the stack then. Let's say you're requesting a web page.
Sure. At the very top, you have the application layer, which uses HTTP. That protocol dictates how the web browser and the web server format the actual text and images.
But HTTP doesn't know anything about radio waves.
Nope. So HTTP hands the data down to the transport layer, specifically TCP, the Transmission Control Protocol.
And TCP is the one that chops the data up and handles the reliability, right?
Exactly. TCP manages the conversation, numbers the pieces, and makes sure nothing gets lost. Then TCP hands those numbered pieces down to the internet layer, to IP.
The Internet Protocol.
Right. IP adds the global routing addresses so the message can find its way across the internet. And finally, IP hands it down to the network access layer, like Ethernet or Wi-Fi, which handles getting it across the actual physical local network.
Here's where it gets really interesting to me. The text talks about encapsulation and de-encapsulation.
Oh, yeah, the nesting process.
Right. I was looking at the visual in the source, and it's basically like putting a letter inside an envelope and then putting that envelope inside a larger FedEx box.
That's exactly it.
Because the user data, the web page, is encapsulated or wrapped inside a TCP segment. And then that TCP segment is wrapped inside an IP packet. And then that IP packet is finally wrapped inside an Ethernet frame.
Yeah, and at each step, the protocol is adding its own header with its specific instructions. And actually, the Ethernet layer adds a trailer at the end, too, just to check for physical errors.
There's a ton of packaging.
It is, but it's totally necessary. And the real magic is de-encapsulation. When all that packaging reaches the destination server, the exact reverse happens. The server strips away the Ethernet frame, then it strips away the IP packet, then the TCP segment, until the pure data is finally handed up to the web application.
And every device along the path, like the routers, they only open the specific layer of packaging they need to see where to send it next, right?
Exactly. They just read the agreed-upon protocols to forward the message.
Okay, but with all these incredibly intricate rules, who actually decides them? Because looking back, why isn't there just a chaotic mess of, 50 different totally incompatible internets?
Well, we actually almost had that.
The protocol wars.
Yes.
Yeah.
Back in the 70s and 80s, big tech companies really tried to own the network.
Yeah, the slides mentioned Apple had AppleTalk in 1985, and Novell had NetWare in 1983. And they were totally proprietary.
Completely closed off. Apple devices could only talk to Apple devices. If you wanted to network them with a different brand, you were in for a world of pain and expensive translation hardware.
But they eventually had to abandon those proprietary systems for TCP/IP in the mid-90s, right?
They did.
So what does this all actually mean? Why did they cave? It reminds me of the car tire analogy from the source material.
Oh, that's a good one.
Yeah, just like car manufacturers have to ensure their tires actually fit standard rims no matter what car you buy, network vendors realized they had to use open standards so their products could interact.
Exactly. Which raises an important question. What happens when one company tries to monopolize the rules of the internet?
We get silos.
Right. And to prevent that, The industry relies on open, nonprofit standards organizations to agree on the rules instead of one company dictating them.
Like alphabet soup of organizations.
It really is an alphabet soup. For the Internet standards, you have ISO-C, the Internet Society, which handles the broad global evolution of the Internet.
Okay, ISO-C.
And then the IAB, the Internet Architecture Board, manages the overarching architecture.
Right.
But the people doing the real heavy lifting for the tech are the IETF, the Internet Engineering Task Force. They're the ones who write the rules via RFCs, or requests for comments.
Okay, I want to pause on the IETF, because their whole philosophy is so cool. I read that they operate on this principle of rough consensus and running code.
Yes. They don't wait for absolute perfection or unanimous agreement. They get a rough consensus among the engineers, prove that the code actually works in the real world, and then implement it. It prevents corporate gridlock.
I love that. And then there's the IRTF for long-term research, right?
Right, and that's just the software side. You also have the Electronics and Communications Standards organizations handling the physical hardware.
Like the cables and the radio waves.
Exactly. You have the IE standardizing Ethernet and wireless LANs, the EIA handling electrical wiring, the TIA for cellular and satellite, and the ITUT for video and broadband.
That is a lot of cooks in the kitchen.
It is, but they manage it all using reference models, specifically the OSI and the TCP/IP reference models.
The layers.
Right, because you can't visually watch a data packet travel across a wire like you can watch a physical car on an assembly line. These layered models give all these different engineers a shared vocabulary.
It isolates the changes, right? Like if someone invents a new Wi-Fi standard, they don't have to rebuild the entire internet. They just change that one specific layer.
Exactly. It fosters massive industry competition because companies can innovate at one layer without breaking the whole stack.
It really is incredible when you step back and look at the whole system.
It's a miracle it works as well as it does, honestly.
It really is.
Yeah.
So to wrap this all up, the next time you effortlessly open a web page on, say, an Apple laptop, and that page is being served by a Linux server halfway across the world, just think about the incredible journey of that data.
Yeah.
Remember the massive stack of protocols, the encapsulations, the nesting dolls of data, and all those open standards working completely behind the scenes just to make that simple digital handshake possible.
It's easy to take for granted.
Totally. But I want to leave you with one final thought to ponder based on that history lesson we just went through.
Oh, the protocol wars.
Yeah. We saw how massive tech giants, Apple and Novell, they had to surrender their proprietary languages in the 90s to adopt the universal TCP/IP standard just to survive. TCP/IP won, and it runs our world today.
Right.
But looking to the future, our networks are expanding in ways they were never originally designed for. We're connecting billions of tiny, low-power IoT devices. We have AI systems. We're even building an interplanetary internet.
Oh, yeah, delay-tolerant networking.
Exactly. Sending data to Mars where it takes minutes for a signal to reach, which totally breaks TCP's requirement for instant acknowledgement.
It definitely does.
So as we push these boundaries, will the TCP/IP standard we rely on today remain our universal language? Or will we eventually be forced to invent an entirely new set of rules to handle the communication of tomorrow? Something to think about the next time your Wi-Fi struggles to load a video. Thanks for joining us on this deep dive.